Well, welcome. In this video, we're going to be looking at the second half of this lesson on transformations. So remember, in the first part of the lesson, we learned about translations, a certain type of transformation, where we move the graph left, right, up, or down. Okay, so that's one type of transformation. We also talked about flipping the graph horizontally or flipping the graph vertically. In this video, we're going to look at how do we vertically stretch or compress a graph. Okay, so in this first box up above there, it basically explains what we're doing. Now, it's kind of complicated, so I want to make sure that you understand it. So first off, if we're going to stretch a graph vertically, that means that we're going to have this letter A, that'll be a number, that's part of our equation. So for example, if you look at that table of values there that we have under example 3a, notice the middle column has 2 times the absolute value of x. That 2, it's outside of the parent function. Okay, so that 2 is bigger than 1. So anytime we have an a value that's bigger than 1, it's going to stretch that graph vertically away from the x-axis. Now, if a is a decimal or a fraction between 0 and 1, now it's got to be a decimal between 0 and 1. So if it's like 3.5, it's a decimal, but it's still bigger than 1, so then it'd be a vertical stretch. But if it's a decimal or fraction that's between 0 and 1, it's going to compress the graph. It's going to squish it down vertically closer to the x-axis. So I wanted to have this video of me so that way you could see those what I mean by stretching it away from the x-axis or compressing it closer to the x-axis. So let's look now at how we would complete this table to get these other graphs. Now, the first one there is done for us. They're the parent function. So again, this is the parent function for what we call the absolute value function. So all the other absolute functions are going to be based on this one that's graphed here for us. Now, it does keep going in both directions, so I just want to make sure you understand that. All right, so we're going to use these same values for x. So these numbers that are here, we're going to use those same values to find the y values for both these other functions. So let's start with that middle one. So if I put negative 4 in there for x, now what the absolute value does is it takes whatever's negative and makes it positive. So the absolute value of negative 4 would be a positive 4. Multiply that times 2, and we end up getting 8. When I put negative 2 in there for x, the absolute value of negative 2 becomes a positive 2. And 2 times 2 would be 4. So that would give you, so our y value would be 4 there. The absolute value of 0 is still 0. So 2 times 0 is just 0. And the absolute value doesn't change a positive value. It keeps it positive. So 2 times 2 would be 4. And the absolute value of 4 would still be 4. 2 times 4 would be 8. So when I go to graph those, when x was negative 4, y is 8. That's way up here. When x is negative 2, y would be 4. So that point would be here. And 0, 0 would be here. And when x is 2, y is 4. When x is 4, y is 8. So this, whoa, let me fix that. There we go. That would be that middle function. So y equals the absolute, or 2 times the absolute value of x. Let's look at this last one in that column. So it's taking, so now our a value in front is half. So we're going to take the absolute value of x and then take half of it. So the absolute value of negative 4, oops, sorry, there we go. The absolute value of negative 4 would be 4, and half of 4 would be 2. And absolute value of negative 2 would be a positive 2, and half of 2 would be 1. And half of 0 is still 0. Remember, if I put positive 2 in there, it stays a positive 2. The absolute value of positive 2 is still 2, and half of 2 is also 1. And again, when we take the absolute value of a positive 4, it stays 4, and the half of 4 would just be 2. So when we go to graph this one, when x is negative 4, y was 2. When x was negative 2, y was 1. Again, I'm using these values and these values to get those coordinates. We have 0, 0. When x was 2, y was 1. When x was 4, y was 2. So remember what I said at the beginning? When our a value is between 0 and 1, it's going to shrink the graph or compress the graph vertically, which is what happened with our green graph compared to the original parent function in red. And when our a value is bigger than 1, it's going to stretch it away from the x-axis, which you can see that's happened to the blue graph when you compare that again to the parent function that's in red. So there's some similarities here. The domains for all of these are negative infinity to infinity. And the range for all of these start at 0 and go infinitely up. And f is referring to the parent function. So the domain and range didn't change despite the fact that we either stretched or compressed these graphs. And that's what this is saying as well. So function h was the last one we did. All right, we're going to skip this next section because horizontal stretching and compressions is not something that we see very often, so we are not going to concern ourselves with that. So we're going to end by looking at what happens when we put multiple transformations in one function. So before we do that, I just want to summarize what we've been talking about. So we have absolute value functions. When we see absolute value functions, they're going to be in this form where we would have y equals a times the absolute value of x minus h plus k. Or we could have a parent function being a quadratic, in which case, when we deal with transformations, the form for that would be y equals a times quantity x minus h squared plus k. And for both of these, our a values affect the graph vertically. So remember, that's where if a is negative, it's going to take our parent function and flip it. By the way, the parent function for this looks like this v. So an easy way to remember that is the absolute value. Emphasize the v in value, and you'll remember that it's v-shaped. So if a is negative, it's going to flip it vertically. If a is a number bigger than 1, it's going to stretch it vertically. If a is a number between 0 and 1, it's going to compress it vertically. And then we have our h and k. So remember, whoops, I have a highlighter there. For some reason, that's not working. But anyhow, for these, the h and k, that's going to affect the graph horizontally. Remember, with the h, we do the opposite. So if it says x minus 3 in absolute value or x minus 3 in parentheses squared, the minus means that we actually go to the right 3 units. Where what happens outside the parent function, that happens exactly as we see it. So if it said plus 5, it means it moves up 5 units. So let's look at these examples. So it says what transformations are applied to the function g of x for these absolute value functions. So for this first one, we would say it's going to move, this plus 3 means that it's going to move to the left 3 units. That 1/2 that's outside there, that means it's going to be compressed vertically by 1/2. So it's going to be compressed to be 1/2 the size vertically. And the last one there, the plus 2 means it's moving up 2 units. Horizontally, it's not moving at all. Okay, so it's a horizontal shift of 0, it's not moving horizontally, but vertically it's moving up 2 units, and then that negative that's in front means it's going to be flipped vertically. Can't spell. Or you could say it's being flipped over the x-axis, but it's going to be a vertical flip. All right, so this is based on the parent function, y equals the absolute value of x. It says a scenic train makes trips on an old mining line. The graph shows the distance y in kilometers, x minutes after the ride begins. How does the graph compare to the graph of the parent function? So we can see that it's been flipped vertically. Again, the original function would look something like that. So we can see that been flipped vertically, and then it's been moved, that vertex has been moved to the right 15 units. So just say it's going to the right 15 units, and that vertex has been moved up also 15 units. So we want to find a equation in this form. That's basically this is asking for. We want to write an equation in that form. So let's use what we just said. It's got a vertical flip. So we're going to move to the right 15 and up 15. So if it's going to be a vertical flip, we'll just say it's a negative. It's not stretched at all vertically. I'll show you how to tell that in just a second. But there's no vertical stretch at all. So we would just have y equals negative. And then it's moving to the right 15. So it'll be x minus 15. Then it's moved up 15 units. So here's how we could tell if it's been moved up. I'm sorry, if it's been a vertical stretch at all. So the original function, if you were to pick a point, okay, so like this point here, we would go to the right one, up 1 unit for that point. If we were to pick this point, it's going to move to the right 2, up 2. So that's for the parent function, y equals absolute value of x. So I know it's been flipped, but I want to see, does it have that same ratio? Does it move to the right 1, up 1? Does it move to the right 2, up 2? Or in this case, if we go to the right, it's hard to see here, but we're counting by, let's see, this would be, looks like, 50, so this would be 15. So going from here to here, this would be 3 units. Okay, so going from 15 to this line here, so going from 15 to 18, that'd be 3 units. Then do we go 3 units down? Well, if I go down 3 units, I would be at 12. And sure enough, that point is at 12. So we're going to the right 3, down 3, okay, which means that it hasn't been stretched at all vertically, so it just stays the same value. It's just being flipped vertically, so we'd have y equals negative quantity x minus 15, the absolute value of x minus 15 plus 15. So that would be our final equation. So that's it for these notes. So hopefully that's enough to help you be able to be successful with doing your assignment for lesson 1-2.